Thank you, Peter, and good morning, everyone. So while we wait for the first slide, I'm coming from a Nansen Environmental and Remote Sensing Center, which is a rather small non-profit research institute affiliated with the University of Bergen. We are 60 people there, of which 40 are scientists, and we work along 3 pillars: climate, ocean modeling and data assimilation, and satellite oceanography. So today I shall take you through these satellite elements of satellite information for polar and marine application. I will give a brief introduction, then show some recently new capabilities and findings, and sum it up. So the satellite oceanography relies on the use of the electromagnetic spectrum. There should be a rotating Earth there, but I'm afraid it doesn't work. But a satellite travels around the Earth 7 kilometers per second and makes one trip in 100 minutes and can therefore make 14 trips in a day. For high latitudes, we need to use polar orbiting satellites. If you were around equator, on the other hand, you have the geostationary satellites, but they cannot be properly used at high latitudes. So we need to combine geostationary and polar orbiting satellite, and we operate that in the electromagnetic spectrum from high frequency, which is nanometers, up to low frequencies, which is microwaves. High frequencies cannot penetrate clouds, and although today and yesterday is excellent weather regimes in Bergen, Norway is known for being very permanently cloud covered. So we are operating mostly in the low frequency microwaves region where the capacity is to penetrate clouds. And Norway has invested a lot of effort into this in respect to satellite receiving stations. And we are the only nation that can have no blind orbits, no blind polar orbits. So we have the satellite receiving station at Svalbard at approximately 79 degrees north. As satellites, they are global. They do repeat. The data are available almost in near real time. The shortest time difference between acquisition and having the data projected in front of you on your computer is in Norway 8 minutes. But typically it's ranging between 30 minutes and 3 hours. Satellites are only seeing the surface, and that's a limitation in oceanography in particular, because we need to draw a 3-dimensional picture of the ocean. Hence, we have to rely on in situ observations as well, and it's fundamentally important that the observing systems is built around that combination of satellite observations and in situ observations. So what I will do now is to try to show you a little bit of the new findings that we have achieved in the last 3 to 5 years. I will use surface current, sea level, sea surface salinity, and sea ice as examples. Satellites can also provide observations of sea surface temperature, vector wind, sea state or waves, and ocean color, but I'm not going to touch on that today. What you see here is the map of the geoid of the Earth. This is given in a unit of height above a reference ellipsoid. And what you notice are that the high regions here, this is where there is a lot of mass inside the Earth that has a strong attraction. Whereas the areas of low is where the in situ part of the inside of the Earth has less mass and less attraction. So the geoid is responding to that. It's a surface of no gravity gradient. Now, what you see here is the map of the mean sea surface, measured from altimetry and combined with tide gauges. And immediately to see that, wow, these two surfaces are almost exactly the same. And yes, that's true, they should be almost exactly the same. The spatial resolution here is in the order of 100 kilometers for both of these maps. If I now take the difference between these two maps, we get this surface. And this surface only ranges between minus 1.5 to plus 1.5 meter. It's called the mean dynamic topography of the ocean. And ocean surface currents, which is in geostrophic balance, has to respect this topographic relief. It means that in the Southern Ocean, the Antarctic circumpolar current goes from west to east because of this strong boundary here, height difference between the cold, or between the blue and the warmer colors. Similarly, you can see the Gulf Stream present there. You can see the Kuroshio here, the Agulhas and the return current, and plenty of other features. So this map is incredibly important in oceanography because it gives us a first picture of the global mean sea surface geostrophic current. If we look at that, we can take that topographic relief and immediately produce that sea surface geostrophic current, basically as it's related to the gradient in the topography. We have a band near equator where we cannot utilize this assumption of geostrophy, but apart from that, now what you see are more details of the different known strong current regime in the world oceans. And among these, again, you have the Agulhas current, the return current, the Antarctic circumpolar current, you have the Kuroshio, the Gulf Stream, you have the Malvinas, and plenty of other features, plus the equatorial current and countercurrent. The magnitude of these is only in the order of 40 centimeters per second. Remember, this is a mean state of the current integrated over periods of 10 plus years. It's important also to notice that if we know this mean current precisely, then we have a much better chance to detect precisely the variability. And it is the variability in the ocean currents on annual, decadal, as well as seasonal timescale, which is of importance for us in terms of considering how the currents changes with climate, and eventually how the current variability influences changing climate. If we go to the Gulf Stream, what you notice here is again you notice again the same pattern of the Gulf Stream here. So you see the magnitudes are up 40 centimeters per second in the reddish. What we have compared it to here are climatology of surface drifter data in gray for these particular points along the path of the Gulf Stream and its extension into the Northeast Atlantic current, plus the return of the cold water from the Arctic through Greenland and the Beaufort, the Baffin Bay, Labrador Sea. And you see the differences here between Nila in gray and GOES in blue. And we take also the other gravity satellite into the account here, which is in the green. And you slowly start to see that some areas, the blue is in closer agreement with the gray if we assume that the drifter data is the true. Of course, it's climatology, so it's not necessarily the true, but all in all, we see there is a sort of a tendency for these blue and gray to agree slightly better than the green and the gray. The reason for that is that the green is too coarse to basically take on this job, to do this sort of comparison. What you now see is basically that we can also fly HF radars in satellites. So this is basically Doppler shift observed from a satellite. And what you notice is, again, the Gulf Stream and its extension into the North Atlantic. You see also the loop current in the Gulf of Mexico, plus the Florida Strait current. The magnitudes of these, on the other hand, is in the order of 1 meter per second or more. This Doppler shift detects basically the surface motion more purely, whereas this velocity field is an integration of the upper, let's say, 10 to 30 meters. Hence, you do have a difference in speed between the two observation techniques. But it's not either or, it's both here. We need to combine them both. And this particularly may be quite powerful in the coming years when the European Space Agency is going to fly its new Sentinel mission, which will provide this sort of feature in the observation framework and give that to directly out to the users to play with. The variability, of course, in these currents is what we also need to monitor regularly. And from satellites, it's done over the years with altimetry, with sea surface temperature detection. And recently also we got the opportunity to measure sea surface salinity. This is in the L-band microwave region, so it's a 20 centimeter long wavelength. And it works very well in these turtle waters where you have the known thermal conditions and where the L-band microwave is sensitive to salinity. And here you notice the salinity field in color, and you have the vectors on top, which is from altimetry. It's an integration over 15 days, and it shows that this can be done systematically over and over again with a temporal resolution in the order of a week to 15 days. There are no cloud influences on this sort of observation techniques. And you see the meandering Gulf Stream, and you see the loops into the warm rings and to the cold rings, cyclonic, anticyclonic. And it's highly needed to see this map in comparison to the mean map in order to understand the total signal of the surface current variability. Altimetry can also measure sea level. And here you see a global sea level map, the trend, in fact, from 1993 to 2010. And you see all the colors more or less are in this light yellowish part here, meaning 3 millimeters per year, roughly. But there are departures from that, and some of that is found in strong current regimes where we have to be very much concerned with in the interpretation, because it could mean just that the shift in the frontal position of the currents can lead to these signals. But in the other places, in the basins, it's more easy to interpret. So 3 millimeters per year from altimetry is what we see now, more or less. If you move this up to the higher latitude, the Nordic seas and the Arctic Ocean, you have in blue tide gauge stations along the coast of Norway. Then in black you have altimetry, which is now co-located with these tidal stations. And you see a rather good agreement between them. And there are trends, which is in the order of 3 millimeters per year, as was mentioned in the previous slide. And in fact, for the altimetry along the coast here, we are up to 4 millimeters per year. Grace shows this signal. This is gravity changes, and it's mass changes, that is. And if you have mass changes in the ocean, it could mean that you put more fresh water to the ocean. And you see the signal of that here. And it shows a trend of nearly 3 millimeters per year. The Greenland ice sheet is, of course, the reason partly for that, what we observe in these waters. It undergoes changes, as we know, and currently we have now, over the last 20 years, seen a significant decline in elevation below 1,500 meters from altimetry. Above 1,500 meters, there's still enough snow accumulations in wintertime to sustain the melting in summer. So the elevation slightly increases or stays flat. But altogether, this is the map, and it goes down. We know it loses in the order of 250 gigaton per year on average, which is given from Grace. This, together with the sea ice conditions in the Arctic, is again influencing our sea level. Less ice means more waters open to heating from shortwave incoming, And altogether, that will give an effect on the steric height and sea level. We know this curve now. We've been monitoring this from satellites for nearly 30 years. And you see the large minima in 2007, which was beaten by the large minima in 2012. This is 2007, this is 2012, and this pink line that you see here is sort of the climatology mean, if you want to say so, which was the conditions from 1979 to 1996. It's not just this that we need to know. We need to know the volume. And to know the volume, we need to measure the height, the thickness of the sea ice. This is done with ISAT, and it's pioneered by people in JPL. And here you can see 2 time series of sea ice thickness from ISAT, where the green is the summer ice thickness and the blue is the winter ice thickness. It's partly randomly covering inside here because ISAT is a laser altimeter. But the worrying thing here is that these 2 guys are merging. And it does tell the true story. There are more and more young ice in the Arctic that is not able to sustain the winter. And hence, the thickness between these 2 becomes more or less the same. This is Gray's contribution to the sea level, equivalent sea level in the Arctic regions over the last 8-9 years. And you notice a clear loss of ice over Greenland ice sheet means that the geoid here becomes changed, and it's less attracting, and hence the water around ceases to be sucked onto the Greenland ice sheet continent, and hence it declines, and it increases on the shelf in the Arctic quite significantly. This is the equivalent contribution to sea level change from Greenland, and for comparison, Antarctica, derived from Gray's. And you notice that the contribution from Greenland to sea level rise is 0.5 millimeter nearly per year now in this period. And it's much less, not much less, it's 10% less in Antarctica currently. But these are the 2 major sources for potentially devastating sea level rise in the future. The geoid in the high latitude Arctic is now looking like this. This is the first map of this that we ever been able to produce thanks to the GOES satellite mission. And you see here elevation changes in total of about 1 meter, from the high in the Beaufort to the low in the Norwegian Sea and in the subpolar gyre. This again tells us a true story about the circulation regime in these waters. And it looks like this. At the resolution of 100 kilometers, this is what we can draw out of the main path of the currents. And these are weaker currents now. This is in the order of 15 to 20 centimeters per second. And it's very important to understand its mean and the variability in order to have proper quantitative estimates of ocean transports. So we need to compare this with models and to learn from why are they different and how can we sort of piece together models and satellites to better come up with a final quantitative accurate estimate of this. This is just showing the surface circulation. It's not just that which is important for us. For the entire conditions in the Arctic Ocean and in the Nordic Sea in general, basically the ocean volume transport from the North Atlantic current is the key source of the environmental conditions we have. So we need to have a very good, precise estimate of the volume transport of this particular flow. And this is what this can start to tell us something about. So in summary, the gravity missions that has been flown in the last 10 years, GRACE and GOES, has given us a fantastic new ability jointly with altimetry to understand ocean mass changes, to draw new pictures of the geoid, to much better estimate sea level, dynamic topography, and also ocean surface circulation. And it's good to know that NASA has approved a GRACE follow-on that most likely will be launched in 2015. Surface salinity, both NASA and ESA again are flying SMOS and Aquarius, and this is very important to detect the salinity signal of the ocean surface, because together with SST, this is the thermohaline picture, the density of the surface of the ocean. And it's very important to have that picture properly understood. It cannot be done so just with SST information. So the salinity and SST goes hand in hand here. And it allows us to also study spreading of freshwater plumes and precipitation minus evaporation, mixed layer dynamics in the ocean, and even young ice, sea ice. Unfortunately, the sensitivity of this L-band is very poor in cold water, so we cannot use it in the Nordic seas and in the Arctic Ocean. Satellite data is also fundamentally important for operational oceanography as the data becomes available in real time. It's also clear that long time series from satellite are excellent for deriving indicators, boundary conditions, and for providing model validations. And we are seeing more and more now the situation which is at play today is that we no longer work with just one satellite, we work with them all. So synergy is the buzzword for how to sort of take this further and to understand processes in the upper ocean with much better accuracy. Thank you very much.